All right, 3 triple integral examples. In this one, they've done the hard work for us of describing the three-dimensional region E over which we're integrating. So I'm just observing that this is, these are the inequalities that are given. Y ranges between two numbers, X ranges between two functions of Y, and finally Z ranges between two functions of X and Y. So that's a type 1 three-dimensional region, and I can set up the iterated integral with the integrand e to the z over y and just integrate appropriately as I would a double iterated integral. Pay attention to, there's 3 letters floating around, so you really have to pay attention to what you're doing. E to the z over y is the same thing as e to the constant 1 over y times z. So integrating looks like this. Also plug in your bounds very carefully. I just integrated with respect to z, so these bounds are going in for the z variable. Also be careful when you have exponentials. When you plug in 0, you don't get 0, you get 1, so it's easy to drop those terms if you're not paying attention. Okay, now I'm going to integrate with respect to x. I'm integrating the term y e to the x, understanding that y is just a constant. So I forgot I was integrating there. So, and then of course the integral of y is y times x. I plug in my bounds carefully into the variable x, and I'm left with an expression that's just in terms of the variable y. I'm going to do a real quick reminder of integration by parts off to the side because I do have a term y e to the y that I need to integrate with respect to y. So quickly, integration by parts is a technique that helps us integrate integrands of this form. I like to use the chart method just so I can do it really quickly. If you haven't seen the chart method and you want to see it, well, just Google it or ask me. But anyway, there's the antiderivative of y e to the y, and that'll be helpful for completing this problem. So I'm down to an easy integral, just treating things very carefully, and I'll plug in my bounds of integration. As with double integrals, go to Wolfram Alpha and check your answer. So there's so many parentheses and negatives and places that I could go wrong. So just get in the practice of checking your work using Wolfram Alpha. If something's off, just sort of comb through your work and see if you can find your mistake. Oftentimes I can find it quickly as well, so you can just drop me an email or virtually see me in office hours and I can help you through it. When all is said and done, I got e over 2 minus 7 over 6. You go to Wolfram Alpha. As you can see here, the triple integral calculator lets you put in the integrand and the limits of integration, however whatever order you have it in. You can see what integral it is interpreted, and it looks like I do have the right answer here. All right, on this one, they don't set up the region for us. They just describe it as a tetrahedron, so we have to do the hard work of setting this up. I'm going to warn you, these problems are really, really tricky, so make sure that you study this example very carefully, see what I've done, and try and do one fully on your own until you can just master setting these things up. So the first thing I'm doing is drawing the tetrahedron. You absolutely have to be able to get a rudimentary drawing of the tetrahedron, so just follow my lead here, how I'm drawing it. I'm not doing a fantastic job, but I'm just plotting the points carefully and connecting the lines. So I have to imagine this tetrahedron object that is connecting these 4 points, and I need to decide how I want to describe it, type 1, type 2, or type 3. I'm going to go through type 1 for you. You should absolutely do type 1, type 2, and type 3. In fact, grab your favorite tetrahedron and do all 6 integration order types. It's a really, really good exercise. So I'm trying to identify the region in the xy plane over which this solid lives, and then I will express the 2 surfaces that z bounces in between, that tilted plane on the bottom and then the flat plane z equals 1 on the top. So for the green region in the xy plane, I obviously have 2 options. I could express it as, in the language of double integrals, a type 1 or type 2 region. I'm going to start with type 1 here. X goes between 0 and 1, and I see y bounces between y equals 0 and y equals 1 minus x. So now I'm going to come over here and figure out what that bottom plane is that z is bounded by. So I got to go way back to the plane section and remember what I need. I have a point, in fact I have 3 points that plane goes through. The origin is the easiest, and then I need to produce a normal vector. Well, notice that these two vectors lie within the plane, and so if I cross them, they will produce a vector that is normal to the plane. So with those two ingredients, a point and a normal vector, I can create the equation of this plane, x plus y minus z equals 0. So z equals x plus y is the function that I'm after. So I've expressed my tetrahedron as a type 1 region. That helps me set up this iterated integral in the correct order. The integrand was given to me. It's x times z. If I wanted to, for example, get the volume of the tetrahedron, I could put a 1 in the integrand, but they have given me an integrand, and so I'm just dealing with it. Okay, on to the next example. Here, they have set up an integral in a specific way, and I want to try and set it up in the 5 different ways that I can. So I'm just writing out these inequalities by looking at the integrals themselves, and I notice that they have set up a type 1 solid. So I'm going to go ahead and express that type 1 solid in the other way that I can by switching the roles of x and y. So I'm looking at this region in the xy plane that's described by those two inequalities in the red box, and I'm redoing it. So I'm going to have y go between two numbers, 0 and 1, and then I'm going to have x go between two functions of y. Here on the left I see x equals 0, and on the right I see x equals y squared. And z from there is just what it was before. It goes between 0 and 1 minus y. So the integral that is produced from this, the outer two integrals have been changed here, and the inner integral stays exactly the same. The order of integration now is z, x, and y. All right, I just have 4 more to go. Those were the 2 type 1 triple integrals. Let me try and set up this region as a type 2 region. So I'm looking for a region in the YZ plane over which this solid lives. It appears to be this simple triangle in y and z, so there's 2 different ways I could express that. I could have y going between 0 and 1 and z going between functions of y, 0 and 1 minus y, or I could have z going between 0 and 1 and y going between the 2 functions y equals 0 and y equals 1 minus z. Now I have to look at the solid again and figure out what 2 surfaces x is bouncing in between. At the back wall, I see x equals 0, and at the front wall, I see this curved surface that is given to me by y equals square root of x. So I understand that on the front, the biggest that x get is y squared by manipulating the y equals x square root of x equation, and at the back, at the lowest that x gets, x equals 0. And of course, I just rewrite that for my other type 2 inequality. Okay, so now I can set up my triple integrals from these 2 different expressions of the type 2 region. Putting everything where it belongs. Okay, so I think visualizing this is the trickiest part, so make sure that you, as I said with the tetrahedron, study the example very carefully and just let me know if you need clarification over virtual office hours. Okay, type 3, I think this is the hardest. I need to find a region in the xz plane over which this solid lives. And so I'm kind of just like drawing a shadow as best as I can. It's not quite clear just looking at it what the shape of that shadow is, but I can use some algebra to help me. I understand that the ridge of the solid object, that curved ridge, is described by the intersection of the plane z equals 1 minus y and the curved surface y equals root x. So that actually gives me that z equals 1 minus root x. That's the curve in the xz plane that I'm seeing as the shadow of the object onto the xz plane. So I can describe that region in 2 different ways, x going between numbers, z going between functions, and then of course I come up to the object to see the surfaces that bound the y coordinate. It's the curved on the left and the flat on the right, so I've got square root of x on the left and 1 minus z on the right. Okay, so just describe the xz region in the opposite way. Z goes between numbers, x goes between functions of z. So I need to solve for x in terms of z to get that. and then y ranges between the same two left and right surfaces. Okay, set up the triple integrals from these descriptions, and we have all 6 possibilities. So this is an excellent exercise to do with any solid region that you see in the section, as well as with any tetrahedron. It's a really, really good exercise to grab a tetrahedron and try and set up all 6 directions. Let me know when you need help.